Any good engineer or mechanic will tell you you don't use a hammer to turn a screw. It's all about having the right tool for the job. And what's true for hardware? Well, it's just as true for math. When you're staring down a complex problem, there's rarely one single best way to solve it. Instead, you've got this whole toolbox of methods, and each one has its own strengths, its own weaknesses. So let's open up this mathematical toolbox and see what's inside.
Okay, take a look at this electrical circuit. On the surface, it seems pretty simple, right? A couple of loops, some resistors, a voltage source here and there. But to really understand what's going on inside, to figure out the currents that are flowing through this thing, you have to turn this picture into a mathematical puzzle. The real question is, what's the best tool to solve that puzzle?
So here's our game plan. We're going to start with the electrical puzzle itself. Then, we'll check out 3 totally different tools engineers have used to crack it. First up, the classic textbook method, Cramer's rule. Then, a really clever shortcut called Wang algebra. And finally, the modern powerhouse known as MNA. And at the end, we'll figure out how you choose the right tool for the right job.
At its core, analyzing a circuit is really all about translation. You're translating these physical things, resistors, wires, batteries, into a system of simultaneous linear equations. You use these fundamental rules, like Kirchhoff's laws, to lay out the math. Once you solve those equations, boom, you solve the circuit.
And, this is not a new problem, not by a long shot. For as long as we've been building complex electrical systems, we've needed rock-solid ways to figure out what's happening inside them. So over the years, engineers and mathematicians came up with a whole set of fascinating tools, each one born from a different era, and really designed for a different kind of thinking.
All right, so the first tool we're going to pull out of the box is the one you'd almost definitely learn in a linear algebra class or your first circuits course. It's called Cramer's rule, and it's kind of the classic by-the-book solution.
Think of Cramer's rule as a recipe. It's a set of instructions that says for any system of equations, you can find each unknown variable by calculating a special number called a determinant. It's a number you get from the grid of values in your equations, your matrix, and the rule gives you this explicit step-by-step formula to get the answer.
So how does this recipe actually work? Well, first, you lay out your circuit equations in that standard matrix form. Then for step 2, you calculate the determinant of that main matrix. We'll just call it del. Now here's the clever part. To find your first unknown current, let's say I1, you make a new matrix. You just swap out that first column with your answer values. Then you find the determinant of that new matrix, and the answer is simply the new determinant divided by the original one. You just rinse and repeat for every variable you need to find.
And this right here is the main selling point of Cramer's rule. If you've got a small system, just 2 or 3 equations, it is super mechanical and honestly pretty easy to do by hand. You just plug in the numbers, you turn the mathematical crank, and the answer pops right out.
But here's the catch. There's always a catch, right? If this method is so easy, why don't we just use it for everything? Well, this is where our simple, trusty tool starts to show its limits, especially when our problems start getting bigger.
And when I say limits, I mean it hits a complete brick wall. As this person on Stack Exchange puts it pretty bluntly, Cramer's rule is highly inefficient. And look, this isn't just an opinion. This is a fundamental mathematical fact that's just baked right into the method.
This all comes down to a concept called computational complexity, which is just a fancy way of saying how much more work do you have to do when the problem gets bigger. For Cramer's rule, the workload grows factorially. It's an absolute explosion of work. Other standard methods grow polynomially, which is much, much more manageable. Think of it like the difference between a rocket ship and a turtle. Both move forward, but one gets out of hand fast.
So let's put that into perspective. Say you have a circuit with just 10 equations. Not even that big, really. Using Cramer's rule would mean doing roughly this many multiplications to get your answer. That's over 36 million. The problem isn't just that it's a pain to do, it's that this factorial growth makes the method completely and utterly impractical for anything but the simplest problems, even for a supercomputer.
So, way before we had computers that could just brute force these things, engineers needed a smarter way to work. And that brings us to our second tool, a really elegant, very specialized shortcut known as Wang algebra.
This was developed back in the 1930s by a Chinese engineer named Qi-Tung Wang. And it's all based on this symbolic algebra with 2 wonderfully simple rules. Rule 1, any variable added to itself is 0. Rule 2, any variable squared is also 0. Now, I know these rules look a little weird at first, but trust me, they have an absolutely profound effect.
See, here's the magic.
When you calculate a big determinant, you're normally adding up a huge mess of terms, but when you apply Wang's two simple rules, a massive number of those terms just poof. They cancel out or they become zero. This system was specifically tailored for the kinds of symmetric matrices you find all over electrical circuits, and it turns a ridiculously tedious calculation into something a human can actually manage with a pencil and paper.
And this wasn't just some academic curiosity, okay? This was a seriously powerful, practical tool. At the famous electronics company Tektronix, Wang algebra was one of the secret weapons they used to design really advanced circuits, like this bridge T network. The insights it gave them were so valuable that the details were supposedly guarded as a trade secret. How cool is that?
So Wang algebra was a brilliant solution for the human brain. But then the computer arrived. And computers, well, they think in a completely different way. This new era of silicon demanded a totally new kind of tool, an industrial-strength powerhouse built for pure computational efficiency above all else.
And that method is called modified nodal analysis, or MNA. Its goal is completely different from the others. It's not trying to be elegant or give a human any special insight. Nope. Its only job is to take a circuit's equations and organize them into a perfectly standardized format that a computer program can solve as fast and as reliably as possible, no matter how ridiculously complex that circuit gets.
MNA takes any circuit you can throw at it and methodically turns it into this universal matrix equation, A times X equals Z. That's it. A is the circuit components, X is the unknown stuff you want to find, and Z is the power sources. For a computer, solving this is just another day at the office. It's a routine task it can perform at lightning speed.
So there we have it, 3 very different tools for solving the exact same problem. And this brings us right back to where we started, to our main idea. A good engineer doesn't just know how to use the tools, they know when to use them.
This table just lays it all out, nice and clean. Cramer's rule, it's your quick and dirty tool for small problems you're doing by hand. Wang algebra, that's your specialized, almost artistic tool for getting deep design insights, a real gem from the pre-computer days. And MNA, that's the modern workhorse. It powers basically all of our circuit simulation software today, and it eats complexity for breakfast.
In the end, it really is just like a physical toolbox. Cramer's rule is your basic, reliable screwdriver. Wang algebra is like a custom-made jig that makes a really tricky task elegant and simple. And MNA, well, MNA is the fully automated robotic arm, built for massive power and speed. A skilled engineer knows which one to grab.
And that is the real takeaway here. It's never about which method is just the best overall. It's about understanding the trade-offs. It's about really knowing your tools. So the next time you face a complex problem, ask yourself, are you just reaching for the tool that's most familiar? Or are you taking that extra second to choose the one that's actually right for the job?